This is lesson 3.10 on linearization. We're going to be using a tangent line to make a linear approximation to a function at a certain point. This is a really useful tool to be able to use because oftentimes the functions we're dealing with are quite complicated or challenging to evaluate at certain points. But if we can make a simpler approximation to the function, then we can use that to make some get some approximate values that are pretty good. So let's look at a picture to see what we're doing here. So let's say our function is shown in blue. So this is the function here, f of x, that I'm highlighting in blue. And we're going to look at a specific point. Okay, let's call that point, let's say that we are at x equals a. So that would mean the y value here of our function is f of a. You can see that point is labeled in the picture as well. So the coordinates would be a, f of a. So I'm going to label those in green. Okay. All right. Now we also have a slope at that point. The slope of the tangent line would be f prime at a. So the slope of this pink line that I'm highlighting here would be f prime at a. So if I want to write an equation for that pink line, I'm going to use slope point form. Y minus y1 equals mx minus x1. And the coordinates are just going to be a and f of a. And then the slope is just going to be the derivative at a. Okay, so if I want to write that out using the correct notation with a and f of a, it would be y minus f of a equals f prime at a. That's the slope. And then x minus a. So I got the coordinates from the point, and then the slope is just the slope of the tangent line. Okay, so that is going to approximate my function for values very close to the point. So you can see the pink line is actually quite close to the blue line for all of the x values surrounding that point, kind of in this general area here. So the pink line is a pretty good approximation for the blue line for values of x close to a. Okay, so we call this tangent line a linear approximation to the function. It's called linear because it's obviously a straight line, which is linear, specifically at x equals a. So you really only want to use this approximation for values close to a. You can see, you know, at the ends of the graph here, there's quite a difference between the pink line and the blue line, so you wouldn't want to use it for values very far away from x equals a. Okay, so let's go ahead and try some examples. So it says the first example is determine the linear approximation for f of x equals cube root of x at x equals 8. Use the linear approximation to approximate the value of cube root of 9 and cube root of 25. Okay, so let's do this. Okay, so first thing we want to do is find the point on the line function, or I'll just say point on f of x. So they already tell me the x value, x is 8. We're going to plug that into the function to determine the y value. So f at 8 is going to be cube root at 8 equals 2. Usually you want to do your approximation at a place where you can evaluate the function easily. So this one happens to work out nicely because 8 is a perfect cube. So I can evaluate that to 2 pretty easily. Okay, now we need to find the slope of our tangent line approximation. So let's do the derivative of f of x, which would be 1/3 times x to the power of negative 2/3. You could also write this like 1/3 multiplied with the cube root of x squared. It's another way to write it. They're both the same. And let's evaluate that at our point that we're looking at here. So this is going to be the cube root of 8 squared, which is going to be 1/12. So the cube root of 8 squared is 4, and then multiplied with 3, that gives us 12. So this is our slope. The coordinates of our point are 8 and 2. So we can make our tangent line approximation now. And oftentimes we want to use, because it's a linear approximation, sometimes we use L of x to describe it. You could also use y, it doesn't really matter, but in the book we use L of x. So it would be L of x minus 2 equals 1/12 x minus 8. So this is point slope form. or slope point, whatever you want to call it. Okay, notice I've plugged the coordinates of the point in here and then the slope of my tangent line here. Now, to use this linear approximation, often we want to rearrange into y equals mx plus b format, just because it's easier to plug in and use. So let's do that now. So it'd be L of x equals, so I'm going to multiply this in. So it'd be 1/12 times x, and then multiply the 1/12 with 8, and then add 2 to it. So that would give me 8/12. 4/3. Okay, so there's my linear approximation for the function. Okay, now I want to use that to evaluate cube root of 9. So what we want to do here is, this is going to be approximately equal to the linear approximation at 9. So I'm going to plug in 9 into the linear approximation here. So it'd be 1/12 times 9 plus 4/3. And that gives me 9/12 plus 4/3. It gives me 25/12. And I'll convert that to a decimal just so we can compare it to the actual value of cube root 9. So that's going to be 2.083 repeating, or 2.083 if I just cut that off. And if I compare that to, I'll just write in a different color here, compared to the actual value of cube root 9, if you plug in a calculator, is approximately 2.080, which is pretty good. You're only 0.03 off there. So because we're really close to x equals 8, where we made the linear approximation, our linear approximation here is going to be pretty good. Now let's do the linear approximation at 25, which is pretty far away from x equals 8. So let's see how good we are. So I'd plug in 25 into my linear approximation function, and I get, making common denominator there, I get 41/12, which is approximately, if I convert it to a decimal and cut it off, 3.417. The actual value of the cube root of 25 is 2.924. So it's not as good, but that's because we're pretty far away from x equals 8. So the key thing to understand here is that when you're close to x equals 8, then your approximation is going to be pretty good. If you're pretty far away, the linear approximation might not do as good of a job in calculating values. Okay, let's do one that's really common in physics. Determine the linear approximation for f of x equals sine x at x equals 0. So sine x is a function that's easy to evaluate at certain values of x, but other values it's really challenging to do using mental math. At x equals 0, so a point on the line, it is easy to evaluate. The y value is just 0, but at points nearby, then it's quite challenging. So the point on the line is going to be, so f of 0 equals 0. So therefore, the point that we're looking at is, 0, 0. Okay? Because that's the point that they're telling us to do. Okay, now we need the slope of the tangent line. So the slope of the tangent line is going to be f prime of x equals cosine x. So f prime at 0 is cosine 0, which is 1. Okay, so that's my slope. So now I've got a point on the line, I've got a slope, I can make my linear approximation. So L of x minus 0 equals 1, x minus 0. I'm just putting in the zeros and ones just so that it's more obvious. You don't actually have to write them. So I've plugged in here into my point slope form, but I will convert it over to slope intercept form now just by rearranging it. So it's just going to be x. So that's my tangent line approximation, and then we are going to try and use it. So this is going to be L at negative 0.2. And since L of x is so simple here, it's just x, so it's just negative 0.2. Okay, and we can compare it to sine of negative 0.2, and it's actually pretty close. Sine of negative 0.2, if you use a calculator, is approximately negative 0.199. So pretty good. Again, only like a little bit off, about 1,000th off there. Yeah. So it's a pretty good approximation. If you draw the graph, you can see why. So the graph of sine x looks something like this, right? And then the linear approximation is just y equals x. It looks like this. So you can see in this like region near 0, the two lines pretty much lie on top of each other. It's a pretty good approximation near x equals 0. All right, so that's the end of the lesson.